Okay, so now we're going to build up our knowledge of gravitational fields by looking at a variation of something that should be quite familiar to you, gravitational potential energy, and looking at this new term, gravitational potential, which is closely linked to it. So, as we did in GCSE, gravitational potential energy is kind of like a type of stored energy that an object has. By virtue of being placed in a gravitational field, it has the potential for the energy locked within it to be turned into other forms, for example, kinetic energy. And at GCSE, we learnt that if you have an object, a mass, above the surface of the Earth, h, high, then you can work out what the gravitational potential energy stored within it is by using the equation mgh. Mass of the ball, strength of gravity at the surface of the Earth, and height above the Earth. But there's a problem with using this method when we're using proper gravitational field theory, because this term here, g, is only constant if you're looking in a uniform field. If we start to increase the distance away from the Earth, in terms of a radial field, then g will be decreasing. And as we know, it's by a 1 over r squared relationship. So, as a result, we need to tweak things a little bit when we're looking at a radial field. Now, when we start thinking about things like fighting gravity, if my rocket's going to get off the surface of the Earth and rise up against the gravitational pull that's pulling it downwards, it has to do work. It has to do work against gravity in order to be able to move up. In doing so, the rocket is gaining gravitational potential energy. So it does work in order to fight gravity, and in doing so it gains GPE. Now, an important concept when we're looking at gravitational potential energy is where will the rocket's gravitational potential energy be zero? And the only place its GPE can be zero is when the Earth is effectively having no more gravitational pull. And we know that Newton's law of gravitation, F equals g m1 m2 over r squared, the only way we can get that F to be zero is if we make r infinity. So, gravitational potential energy is zero at infinity. And that's an important concept for how we visualise our gravitational potential energy. So, here's our little rocket on the surface of the Earth, and I've changed the colour of it as you go further up. Further away I get from the Earth, the smaller g is getting, so as we go in this direction, g is getting smaller. And that means that if I want to get my rocket from the surface of the Earth to this point here, I'm going to have to put quite a large amount of energy in. I'm going to have to do a lot of work against gravity because g is quite big. If I wanted to get the rocket from this point to this point, g has got smaller. And so that means that the work done to move from this point in the field to this point in the field is less than the work done to move from the surface of the Earth to that point in the field. And again, if I want to move from the orange to the black and blue rocket, g has got even smaller again. So again, the work that I need to put into the rocket to move it that distance, even though it might be the same distance as before, is smaller once again. And so if we were to plot this on a graph over here, because we know that our gravitational potential energy will be zero at infinity, we start plotting on this line. And my first rocket will have zero gravitational potential energy at infinity. As I get closer to the Earth, the gravitational potential energy is going to decrease. Just like in a uniform field, if my object is closer to the surface of the Earth, it has less gravitational potential energy. That's also the case for a radial field. But because I have maximum gravitational potential energy at infinity, that means that as I get towards the Earth, the gravitational potential energy that my rocket has is a negative number. And that's just a convention, because we're starting with GPE being zero at infinity. As we get closer to the planet, the energy has to drop, and therefore the number is getting more and more negative. And so that gives us a nice little gravitational potential energy graph that tends towards infinity, but never actually, it tends towards the zero line, but will never get there until it reaches infinity. And so this means that we can have a new definition for gravitational potential energy. If my rocket is within a field at infinity, gravity will do work to move it closer to the planet. And so my official definition for gravitational potential energy is it's the work done by gravity to move a small object from infinity to that point in the field. And the closer I am to my planet, the more work has to be done by gravity to get me from infinity to that point. Now, technically, it should actually be the negative value of it. And we can also look at this as saying it's the negative of GPE is the work done against gravity to get to infinity. Now, to get an equation for gravitational potential energy, and it's important to note here that you are not expected to know this equation for the exam, but this helps us derive the next equation. We know that GPE equals mgh from GCSE. But if we substitute r, the distance from the centre of the planet, for our h, and if we use our gravitational field strength equation, we can combine those two together to give us a term for GPE. And since the r's cancel out, here is our lovely equation. Gravitational potential energy of an object within a radial gravitational field is, and there should technically be a minus sign there because we're starting at 0 at infinity, minus the gravitational constant times the mass of your planet or your star, whatever your origin of the gravitational field is, times your smaller mass over the distance to the centre of the planet from your location. And of course, we're looking at an energy, so the unit's going to be joules. So let's have a quick example calculation for that then. I have a rocket of mass 2,000 kilograms at an altitude of 150 kilometers above the surface of the Earth. And I need to work out what the gravitational potential energy of that rocket is, or how much kinetic energy would it gain in falling from that point back down to the Earth. Well, I know that I'm going to be using the equation energy is equal to minus gmm over r, but that r is not the altitude. We have to be careful with that. That r is the radius of the planet plus the altitude. And why is that important? We always measure our distance from the centre of the object to the centre of the planet. So that means that my r is going to be the radius of the Earth, 6,370. And be careful, because it's given in kilometres, we have to do times 10 to the 3 because we always have to convert into metres, plus my altitude, 150 kilometres. So again, times 10 to the 3 to get it into metres. That gives us an answer of 6.52 times 10 to the 6 metres. So whenever we do these questions, first of all, make sure you've converted back into metres. Now we plug that into our equation. E is equal to minus 6.67 times 10 to the minus 11 times the mass of the planet, which in this case is 6 times 10 to the 24, times the mass of my rocket, which is 2,000 kilograms, divided by the radius that I calculated earlier, 6.52 times 10 to the 6 metres. And when I plug that into my calculator, I get a gravitational potential energy of 1.23 times 10 to the 11 joules. So that's working out the gravitational potential energy, but what we're trying to do here is come up with a model for a gravitational field. And GPE in itself is not great for showing us the true nature of the field. If I've got an elephant and a mouse, both 400 kilometres above the surface of the Earth, and with vastly, vastly different masses, we know they're going to have very different gravitational potential energies. And in fact, when you pop those figures into the calculation, you get that the gravitational potential energy for the elephant is 1.6 times 10 to the 11 joules, and for the mouse it's just 1.2 times 10 to the 6. So if we were to plot a graph of the gravitational potential energy of two differently massed objects by distance, we get two different graphs. They show the same kind of shape. We know it's a 1 over r relationship, but the smaller, less massive object has got a much smaller overall trend in gravitational potential energy. And so this means that I effectively would have to draw a new graph or a new representation for gravity for each individual object. Now, from a modelling point of view, that's not very useful. And so what we do is instead we say, okay, to model this field and to give us something that represents just the field, not the objects within it, we're going to work out what the gravitational potential energy of a single kilogram would be. And so if we plot for the Earth the gravitational potential energy of a 1 kilogram mass, we get this graph here. So I've got GPE per kilogram, or energy divided by mass. And this graph here is what we call a graph of gravitational potential. Gravitational potential is just the potential energy per kilogram, per unit mass. And so this graph represents, if we've got the Earth sat here at the bottom of the potential well, it just gives us a uniform representation of how objects will move due to being in that gravitational field. Now, if I wanted to find the GPE of one of my elephants or both of my elephants, I could use this graph to do that. Because I know that the gravitational potential is the energy per kilogram unit mass, all I have to do is times my potential by the mass of this elephant, and that will give me the gravitational potential energy. If it's got this much energy per kilogram, then timesing the gravitational potential by the mass of the elephant will give me the energy of the elephant. And I do the same for this elephant, times by the larger mass. In all of this, gravitational potential, just like electric potential, is given by the letter V, capital V. And so I basically have a term now that energy of, gravitational potential energy is the potential times the mass of my object. So gravitational potential is how much potential energy each kilogram of mass has at a point in a gravitational field. If we look at the old definition for gravitational potential energy, we can now tweak that to get the definition for potential. If we get rid of the energy, so we've just got gravitational potential, and we know it's the work done per kilogram unit mass, we get our new definition, and this is one that you do have to learn. Gravitational potential at a point is the work done per kilogram unit mass by gravity to move an object from infinity to that point. It is a bit wordy, but it's basically just saying how much energy per unit mass does gravity have to do on an object to move it from infinity to a point in the field. And to get an equation for it, here's our gravitational potential energy equation. Well, we know that it's per kilogram unit mass, so we just divide the whole thing by m. And this gives us that gravitational potential is equal to minus the gravitational constant times the mass of the planet or the large object that is originating the field, divided by your distance from the centre of that planet. And because it's an energy over a mass, or joules divided by kilograms, the unit for it is just going to be joule kilograms to the -1. So here's a quick practice question then. This year, NASA's Juno spacecraft entered into orbit around Jupiter and has given us some amazing images. Now, Jupiter's current orbital altitude is 4,300 kilometres. Given that the mass of Jupiter is 1.9 times 10 to the 27 kilograms, the mass of the Juno spacecraft is 1,593 kilograms, and the radius of Jupiter is about 70,000 kilometres, what is the gravitational potential of Juno at that orbital altitude of 4,300 kilometres? Well, we know that we're going to be using the equation V is minus gm over r. And of course, as before, we're measuring the radius to the centre of the planet, so our r is going to be the radius plus the altitude, which equals 70,000, and it's kilometres, so times 10 to the 3, plus 4,300 times 10 to the 3. And that gives us a radius of 7.43 times 10 to the 7 metres. Now we just stick that into our equation, over here. V is equal to minus 6.67 times 10 to the minus 11 times the mass of Jupiter, which is 1.9 times 10 to the 27 kilograms, all over our radius that we've just calculated, 7.43 times 10 to the 7 metres. And that gives us a gravitational potential of 1.7 times 10 to the 9 joules per kilogram. So that's telling me that each kilogram of mass at Juno's orbital altitude in that field has 1.7 times 10 to the 9 joules of energy. How would I work out what the potential energy of Juno is? Well, I just take the potential, the energy per kilogram, and I multiply it by the mass. And so that means that the energy of Juno is 1.7 times 10 to the 9 multiplied by the mass, 1593 kilograms, and that gives me an energy of 2.7 times 10 to the 12 joules. And that's how you manipulate the equation. It's all about remembering that gravitational potential and potential energy are almost the same thing. It's just that potential gives you the energy per unit kilogram mass, and it allows you to better represent the field. One last thing that we need to look at is finding the work done in moving within a gravitational field, and this is a very common thing they'll ask you. Here at the surface of the Earth, the gravitational potential is about minus 63 megajoules per kilogram. That means if I wanted to bring an object from infinity to the surface of the Earth, I would have to, or gravity would have to do 63 megajoules of work on it to bring it to the surface of the Earth. Or, rather, if I wanted to get an object of 1 kilogram from the surface of the Earth to infinity, I would have to put in 63 megajoules per kilogram to get it to infinity. If a rocket's got a mass of 2,000 kilograms, and I wanted to work out the work done against gravity, or the gain in GPE, for my rocket in going from the surface of the Earth to, let's say, a point in the field where I have minus 50 megajoules per kilogram, and look, even though the magnitude of the numbers got smaller, because it's negative numbers, I am getting higher in my number. All I need to do to work out the work done against gravity is take that difference there, that potential difference, delta V, which in this case here is minus 63 to minus 50. There's a difference of 13 megajoules per kilogram. That means that I would need to put 13 megajoules of energy into my rocket to move 1 kilogram that distance. How much do I put into my whole rocket? I just take my delta V and I times it by the mass. So my 13 megajoules multiplied by my 2,000 kilograms gives me a change in gravitational potential energy, or the work done on my rocket, of 2.6 times 10 to the 10 joules. So if you ever see people talking about gravitational potential difference, it literally just means what is the difference in gravitational potential from one point in a field to another. If my rocket was going up here, I would find that gravitational potential difference. That tells me how much energy I need to put into 1 kilogram to get it that high, times it by the mass of my object, and it tells me how much energy I need to put in to my whole object to get it that high. And I hope that's helped clear a few things up. Certainly it should help with your homework. If you do have any questions following on from that video, please do drop me an email. Don't leave it till Monday. We'll do a lot more on this on Monday and we will practice all of gravity, but I hope that's been helpful to you.